Thanks again for the invite. So today I'll be presenting a talk on language processing on quantum hardware with DisCoPy. So it's joint work with Bob Coecke, Giovanni De Felice, and Konstantinos Mešanetsidis. And we're all affiliated with the quantum group in the computer science department at Oxford. And we're also working with Cambridge Quantum Computing. Yeah, let's get started. So for an outline, today I'll try to keep the slides short and then go to a demo. So first I'll introduce diagrams, so string diagrams, from the point of view of geometry, of algebra, and then from the point of view of data, which is the one that is going to interest us here. And then I'll explain what we can do with diagrams. Essentially, we can apply functors to them, so that I'll explain what that means. And I'll give two examples. One is natural language semantics, and the other is quantum circuit evaluation. So then hopefully I'll get enough time to show a nice demo of DisCoPy working in action on some quantum natural language processing experiments. So both simulations and real hardware, quantum hardware experiments. And then if I get some time at the end, I'll talk about the future directions, or feel free to ask me more questions about that. So let's get started. So what is a diagram? So from the point of view of geometry, a diagram is just a bunch of points and lines on the plane. So on the left, we got the cover of Kandinsky, Punkt und Linie zu Fläche, so where he describes how painting is all made of points and lines on the plane. And on the right, we got planar diagrams and tensor algebra, a seminal paper from the 80s by Joyo and Street, where essentially they give a rigorous definition of a class of diagrams that are found in a lot of different sciences with a lot of different applications. The main one being, the first one being physics. So Penrose started drawing these diagrams, and Joyo Street were the one to first give them a formal mathematical definition. So what is a diagram? It's a bunch of points. So like this A, B, C, and D, and a bunch of lines like this capital A, capital B. And essentially, that's it. So it's a bunch of points and lines on the plane. The small caveat is that we consider them with a boundary. So there's here a left boundary with ABC and a right boundary. So it means we can paste diagrams together, we can put them side by side or one after the other. So why are string diagrams important? Well, because they capture precisely monoidal categories. So what is a monoidal category? Essentially, it's a collection of processes that you can draw diagrams for. So what does that mean? Well, essentially the intuition is we've got systems and processes between them. So a system we're going to represent as a wire with an arrow going from here left to right. So T is a system and S is a system. And when we tensor them, it means we're just putting the wires side by side. So mathematically, we're going to write S tensor T, and diagrammatically, we're just going to draw one wire next to another with the labels. So we've got an empty diagram, which corresponds mathematically to the unit object of our monoidal category. And essentially, it means that if I have a system and I put nothing next to it, then it doesn't change anything. So next, we have morphisms. So morphisms, they can be represented as points, as we've seen in the previous slide. They can also, more commonly, they're drawn as boxes. So these boxes are going to have a number of wires coming in, here A1 to AN, and a number of wires coming out from B1 to BN. And that's it. So that's a morphism. It's what we call a box in DisCoPy. So I'll explain what you can do with those or what they mean. But the main thing that you can do with these boxes is you can plug them one after the other. So for example, if I have a process that goes from A to B, so S in this example, and an S prime going from B to C, then I can plug them one after the other, and I get a diagram with two boxes from A to B to C. And if I have two diagrams, I can also put them side by side. So in this example, it's going to be the tensor product. Mathematically, it's going to correspond to the tensor product of S and T. So now there's one equation essentially that rules these diagrams, is that you can slide a box along its wire. So that's what the equation at the bottom says, is if I do F and then I do G and they have no wires in common, then it's the same as doing G then doing F. And essentially that rule captures the fact that if F has no side effect, then F and G have no side effects and they don't influence each other, then it doesn't matter which one happens first. So that's what we mean by having two processes in parallel. So diagrams are first a geometric object. There are things that you draw on the plane, and then they also have an algebraic content. What that means is you can describe these diagrams as equations, more precisely as equations that describe arrows in a monoidal category. So anything that you can build out of essentially the empty diagram and a bunch of lines that we call identities, and then tensor and composition. So there's a lot of different flavors of string diagrams, like are you allowed to cross wires or not? Are they, like, you can add a lot of gadgets to your diagrams, and there's essentially a big zoo of diagrams. And there's this really nice survey by Salinger on the graphical languages of monoidal categories. So I'll refer to that for more technical details. So here I'll try and be quick, and I won't spend so much time introducing the mathematical definitions. So let's go directly to the Python definition. So essentially, the starting point is an implementation of string diagrams. So we've got a bunch of Python classes. We've got a class for objects. So these are the atomic wires, the single wires of our diagrams. Then a type can be multiple wires pasted together. So x1 up to xn will be objects. And then we've got a box. So what is a box? Well, a box has a name and it has a domain and a codomain, which are types. So essentially, that's the Python implementation for what I've just drawn before, a box which takes any number of wires in, any number, and leaves any number of wires out. And it's just got a name, so the label in the box. And so technically we need to define what a layer is. So that's just going to be one slice of our diagram. And what that is a box in the middle and then a bunch of wires to its left and to its right. So for example, here I have a layer with a wire X on the left, a box G in the middle, and nothing on the right. The layer after will be a box F in the middle, nothing on the left, and a wire on the right. And now, what is a diagram? Well, a diagram is going to have a bunch of wires coming in, the domain. It has a bunch of wires going out, the codomain. Then it has a list of boxes and a list of offsets. And offsets essentially tell you how many wires are to the left of each box. So the offset of G in this case will be 1, the offset of F will be 0. And essentially, under the hood, if you just give me boxes and offsets, DisCoPy is going to calculate a list of layers. So you can also give that as input, but it's optional. So let's just look at the syntax and how you use it. So you import everything from DisCoPy, then you create X, Y, Z, W, a bunch of types. Now you can create boxes specifying their input and output types. So F goes from X to Y, G goes from Z to W. And you can write any complicated expression for a diagram using this at is the tensor product, and that's as close as we found in Python. And the double greater or equal is the composition. So that is kind of close enough. So anything that you can build out of boxes, identities, composition, and tensor is a diagram if it type checks. So if you don't get any type error from Python and you build a valid diagram, you can draw it. So this diagram is going to correspond to the figure on the right. And now you can use DisCoPy as essentially an algebra system to check equations between different diagrams. So check equations of monoidal categories. So for example, this diagram that I've written, you can also define it directly. Instead of using the formula, you can just specify the domain, codomain, boxes, and offsets. And you can also check that, essentially you can check that two diagrams are equal if they have the same normal form. So that's just, essentially it takes a diagram and moves boxes around so that you can check that two diagrams are equal. So that's useful, but it's just essentially abstract mathematics. So how do you make it concrete? Well, let's go to the next slide. So what can you do with a diagram? Well, you can apply a functor to it. So the functor is going to be the essentially the second data structure of DisCoPy. And how you instantiate a functor, you give it a dictionary for objects and a dictionary for arrows. So the dictionary is going to send every basic object, so every wire, to another object. So it could be a number of wires, or it could be something else. So that's what ob factory or r factory do, is essentially you can define functors that, instead of just drawing diagrams, do computation. So the main example that we've been working on is natural language processing, where essentially we start from this diagram on the left is representing the grammatical structure of a sentence. So here we've got Alice loves and Bob, and we know that Alice is the subject of loves and Bob is the object of loves, and that gives us a sentence. So you can take this diagram and essentially replace every triangle here with a vector. And now computing the value of this diagram essentially is going to replace every wire by a vector space and every box by a linear map or a matrix. And that means that you draw the diagram, you replace every box, every word by its meaning. So a vector for nouns, or a matrix for verbs, etc. And what you get as the application of the functor is the meaning of the sentence. So I'll show an example of that just after. And the second example of what you can do with DisCoPy is you can draw any quantum circuit. So here's an example on the right of a quantum circuit where we've got a bunch of kets. So that means I'm preparing a qubit. And then we've got quantum gates like H, which takes a qubit and rotates it. And we've got this CX, which takes two qubits and entangle them. And then we also have scalars around, and we have bras, which essentially do measurements and post-selection. So if that doesn't make any sense to you, I'll explain more of it in the demo. So essentially what we've been doing with quantum natural language processing is we've been implementing this DisCoPy library that can implement any monoidal category. And now the grammatical reductions of natural language live in a monoidal category. Quantum circuits live in another category. And what a functor can do is it can take your sentence and translate it into a quantum circuit that computes its meaning. So essentially that's what happens here. On the left, we've got a sentence with a bunch of words and how they're connected together, the grammatical structure. On the right, we've got a quantum circuit that is going to compute the meaning of that sentence. So here, the block on the top would be the meaning of loves, and this ket 0 is the meaning of Alice, this ket 1 is the meaning of Bob. So here's a bit of a trivial example. And essentially what happens with these cup-shaped wires, so these bent wires, is that in quantum mechanics, they will correspond to the Bell effect. So essentially what's happening here is that we're using quantum teleportation to send the meaning of a noun to its verb, and essentially using quantum teleportation, we're computing the meaning of sentences. So yeah, I think that's what I have for the slides. So I'm not gonna explain any more maths, and I'll just go to the repo. So okay, the link doesn't want to open. Oh, it does. So here's the repo. We just got to 100 stars on GitHub, so we're really happy, and we're still working on it. So there's a lot more features coming. And yeah, it's got a bunch of documentation, and there's an archive, a paper on the archive that explains both the maths and the code behind the library. And well, the most important thing for us is going to be the notebooks. So we have plenty of them, and so the one I'll be showing, well, the one I would want to show is the QNLP experiment notebook, where we actually do what I've just said on real quantum hardware from IBM Q. And well, that's probably not gonna work out in a Zoom meeting. So, well, I mean, calling IBM Q and waiting in the queue for the quantum machine is probably gonna take too long. So first, I'll go through the same experiment using a simulator instead. So, right. So here's my notebook. So I'm going to import types and words. So what is a word? Essentially, it's a box that has a name like Alice and a type, its grammatical type. So here, noun. And for verb, it's going to be a complex type, like it takes a noun on the left, it takes a noun on the right, it gives you a sentence. So that's the idea. So you define your words, you define your basic types first. And now you have your vocabulary. You can ask DisCoPy to look for grammatical sentences. So Alice is rich is a grammatical sentence. Bob is rich is one as well. Alice loves Alice. Alice loves Bob. Alice, who is rich, not very interesting, but that's grammatical as well. So we'll just brute force through all the grammatical sentences. It's going to take a bit of time. And so what are we going to do with these sentences? Essentially, we're going to use these random or these brute force sentences as a corpus for our experiment. So we're going to take all of these sentences and we're going to turn each of them into a quantum circuit. This quantum circuit is going to have parameters defining it. So each word has a set of parameters that define a bit of circuit. And when you want to get the meaning of the sentence, you take the meanings of the words and you plug them together along the grammatical structure, and that gives you the circuit for the sentence. So every word comes with parameters, and that means we can use essentially quantum machine learning to learn those parameters so that we can capture the meaning of sentences that comes from a corpus. So in our case, it's going to be a toy corpus. And well, the brute force is taking longer than I was expecting, but that's okay. I'm done. Okay, so we've got a lot of sentences here, or 20 sentences, I think. It's a really small corpus, but it's going to be enough for our demo. So let's draw one of them. So we've got this complicated diagram with Alice, who loves Bob, is rich, and the grammatical structure for it. Now, essentially, we're going to define this complicated circuit, so this bit of circuit, which prepares a special quantum state called the GHZ state, which is going to be the meaning for the word who. So there's been a lot of literature on how relative pronouns like who can be modeled nicely on quantum computers using this special state. And now I'm going to define a bunch of circuits. So one for the verb is rich, so for intransitive verbs, and one for the verb loves. So the verb loves essentially is going to take 2 qubits in and spit a scalar, so the result of a measurement out, whereas the verb is rich just takes 1 noun and gives a result. So okay, so now essentially we've got 2 dictionaries. Objects is going to send every type of our grammar. So here, sentence and noun to a number of qubits. So nouns are going to have 1 qubit. It's a toy experiment. And sentences are going to have 0 qubits. And what that means is essentially a sentence will correspond to a scalar. So a sentence will correspond to the results of a measurement from a quantum circuit, so that if the results are close to 1, it's a true sentence. If they're close to 0, it's a false sentence. So, right. Now we've got these 2 dictionaries, one sending types to number of qubits, the other sending words to bits of circuits. So Alice gets sent to ket 0 and Bob gets sent to ket 1, loves to this complicated parameterized circuit. well, complicated. It's essentially, it's doing just one rotation. It's kind of simple. But now we've got these two dictionaries. We can essentially build a functor, or more precisely, a function which takes parameters and constructs a functor. And we can apply this functor to, for example, Alice, who loves Bob, is rich. And we get this complicated circuit. So here we can spot the meaning for who, and over there is the meaning of Alice. And that's the circuitry that you need to glue the words together. Now, what can we do with this circuit? Well, we can evaluate them. So essentially evaluating a circuit is, again, applying a functor. It takes a qubit and it maps it to a vector space. So a qubit corresponds to a two-dimensional vector space, and it takes a gate and maps it to a matrix. So for example, yeah, rotations along the x-axis would be an example. So, all right, so we've got our functor. Now we're gonna evaluate this functor on every sentence of the corpus. We're gonna get a bunch of circuits. And for each circuit, we're going to evaluate it. So that's what this corpus does. It takes the sentence, evaluates it, and computes a truth value. So for each sentence, we're going to have something that is either close to 1 or close to 0. And here we are. So the true sentences of our corpus will be Alice is rich, Alice loves Bob, Bob loves Alice, etc. And here are the false sentences. Now we're going to use sklearn to split the corpus into training test and training set and testing set. So that's kind of standard machine learning. Now we're going to use JAX, a library from Google, which essentially allows us to compute the gradient of any Python function, which is very useful in our case because we have this Python function which evaluates a quantum circuit, and it's kind of a complicated function. You don't want to write the derivative yourself, so you ask JAX to do it. You ask JAX to do it. Also, JAX does just-in-time compilation, so it's very efficient for simulation. Or the first time it takes a long time, and then it's going to be very fast. So yeah, it took 12 seconds to compile the loss. So essentially to apply a function on every circuit for the first time. And here we're computing the loss with respect to the original, so with respect to the true parameters. So it's very close to 0. And now what we're going to do is essentially we're going to forget the true parameters, so the parameters that we used to generate the corpus, and start again learning them from scratch. So that's what this cell does. So we're just going to start again from random parameters. And now we're just going to run some vanilla gradient descent to learn the functor. So essentially what that means is we want to learn parameters for loves and for is rich so that we reproduce the original data. So we started from some parameters, param 0, and now we forgot param 0. We start again from random parameters. And at the end, what we want is to converge back to the original thing. So yeah, it went pretty fast. So the first time you run it, it took 12 seconds. Now it's in microseconds. So that's pretty good. Now, is Alice, who loves Bob, rich? Well, according to the parameters that we've learned, yes, she is. So that's a small example of question answering. Essentially, we're taking a question and we're turning it into quantum circuit. And depending on the result of the measurements, we're going to say yes or no. So in our case, it's binary, but you can make it more complicated. And now just to finish with a beautiful picture, we're just because it's a classical simulation and because we can, we're just gonna compute the whole landscape to just see what it looks like. And here we are. So that's the landscape of the loss function for our model, depending on those two parameters for loves and for is rich. And that's what it looks like. So I think the main point of quantum machine learning is that we get different kinds of landscapes than the ones we get from neural network or classical neural network. So here's an example of a landscape for a quantum machine learning experiment. And it gets really hard as the dimensions grow up. So I'll just show the same experiment just to wrap up. I'll show the same experiment, but on real quantum hardware this time. And I guess the one thing I haven't mentioned yet is that to run our diagrams on quantum hardware, we're using the library from CQC that's called Tickets. It's a compiler, and it takes essentially the diagrams and it turns them into code for Qiskit. So that's the library from IBM. So now we've got this Qiskit circuit, and we can essentially use Ticket to do all the job for us to send these circuits on the quantum hardware. We just have to wait in the queue, and I'll show what waiting in the queue looks like. So you just wait for the job status to go to success, and you wait again, and you shoot a lot of circuits to get some update for your parameters until you converge. And at the end, after a long waiting time, what you get is that, is Alice Loves Bob rich? Yes, she is. And I think that's all I have to show.
Thank you.
So for the questions, I guess we don't have any questions in the chat. So
I do have a question.
Okay, great.
I was wondering, I mean, what's the eventual goal of doing it in this diagrammatic thing? What's the advantage doing NLP diagrammatically over doing it just with this, let's call it brute force deep learning GPT-3 type of thing? You take a lot of data, you train a lot of weights, you get some results, you can perform really good on question answering tasks, for example. What's the benefit?
So I guess the benefit for now is hard to see because we're only playing with toy models. So obviously we're not trying to compete with GPT-3 or anything like that. And I guess the main point is that using these diagrams, essentially we make things easier for the quantum hardware. So oh, I was muted.
Yeah, sorry. Yeah.
I was saying those diagrams essentially get you closer to the quantum hardware, and essentially they make the life easier for the quantum hardware. So these trillions of parameters that GPT-3 is going to use, for example, essentially a lot of them are going to be dedicated to learning grammar and to learning how words connect to each other. And here we're giving that to the computer for free. So essentially that's going to save a lot of computation that the quantum machine doesn't have to do. And for now, the quantum machines we have are really bad. So we can't really expect them to do trillions of parameters. And also, I guess it's also a step towards explainable AI. So in a sense, once you have these diagrams, it makes more sense why your model gives this or that answer, in a sense that you can essentially open the black box of your neural network so that it's easier to explain, because now you have these diagrams that show you how the meanings connected to each other, and instead of having just a black box transformer or whatever. So yeah, I guess it's a big topic. I mean, the future directions would be to show that quantum hardware has an advantage compared to classical hardware, and so that's already been shown by Google, but to show that that's true not only for the useless tasks that Google used for their experiment, but for useful stuff. So essentially quantum advantage for useful problems would be the overall, the long-term goal.
Okay, thank you.
Okay. So there is one question from Konstantinos. I think he's your boss, or he's your colleague, I guess.
Yeah, he's a colleague, yeah.
I think he can also, can you want to ask yourself, Konstantino?
Yeah, hi. I just wanted Alexis to give some thoughts on combining, like thoughts on combining diagrammatic formal methods like the ones he showed with ones that are mainly empirically driven, like deep learning. and brute force supported, let's say. Maybe not today, but like in the long run.
Well, I think it's a big question, and we're probably not gonna answer it completely in 5 minutes. But I guess a quick answer to the long question would be that so DisCoPy, the dis and the co come from distributional, compositional. So the compositional stuff is all about these diagrams that show how you compose worlds together, and the distributional part is what comes inside of the boxes for each world. So that's what the matrices are for. That's what the quantum circuits do. So essentially, the aim of these diagrammatic methods are, in the long run, to use all the power of distributional semantics, which is essentially what neural networks do. They learn from distribution of words and how words come in sequences to learn what is a likely sequence or not, or what is the answer to a question. And they do that from a lot of data. And I think for now we're only at the beginning, but the point, I think the most important direction is really this explainable AI idea of not only we want these black boxes that can answer every question, but we don't know why. We want the machine to explain why it gave this or that particular answer. And I think that's what the diagrams would help you achieve.
Okay. I think there's a comment from your boss, Bob. I think is it a comment or is it a bit of a question raised as a comment? Yeah.
No, there's another question from Michael Paris.
Okay.
Michael Paris seems to have a question now.
Before that, Michael, would you excuse me? There is a question from Luke Jordan. Do you want to unmute yourself and ask it, or you want us to read it?
Sure. This might be a bit naive and somewhat general, but it just strikes me there's a lot here that's similar to graphical methods in things like causal machine learning, where it's again, and in fact, graphs and diagrams seem, I'm sure there's a rigorous distinction between them, but they seem quite similar. And when a lot of work in causal machine learning is trying to understand exactly that kind of interrelationships in a way that seems very similar. Is there an overlap? Is that something?
There's a huge overlap. I mean, so Bob has a paper on using these diagrams to do Bayesian reasoning. And I know a lot of people are starting to apply these diagrams and monoidal categories to Bayesian reasoning, to causal inference, to, so there's a big overlap, and I can send some pointers to the literature if you're interested.
Cool, that'd be great.
Okay.
And then there was another question from Space Base on can you use it to learn logical relations, get logic truth out of your data? And so that's basically that's what we've been doing before we implemented this stuff on quantum hardware. We were treating it as a way to essentially turn a question in natural language to a query for a database, so equivalently to a logical formula. And so, this stuff works really well with logic because category theory and logic go really well together. So I could send some pointers for that kind of stuff as well.
Okay, I think before we go with Michael's question again, I think if there are any other questions, we can take them first, or else, Michael, I guess, you want to ask it, or you want to just?
Sure. So in your example, you had to sort of teach the system what the grammar of each word was. For example, the word loves, you defined it as with a specific type, something that takes a noun from the left, a noun from the right, returns a sentence. And wouldn't this be a problem or a disadvantage in a sense compared to GPT, like some general purpose natural language?
So I guess you asked the big question, or the main question that sort of stands in front of us if we want to apply this stuff to real data and not only to our hand-drawn diagrams, is how do we get from text, which is what usual machine learning will take as input, to diagrams? And that's a really crucial step if you want to apply this stuff in practice, right? So if you want the model to be end-to-end, you can't assume that the computer is going to guess the diagrams. So I guess one answer is from like formal language theory is you can train, essentially you can train a model to learn the grammar, and there's a lot of work on grammar induction. So learning the types for each word and learning how they connect. So that's one answer, and it's sort of the traditional answer. People in formal language theory will just use grammar induction first and then a parser, and there's no machine learning involved. Or the direction that essentially we would want to take is to essentially make this grammar induction the first layer of an end-to-end model, where essentially a machine learning algorithm would come to learn how to draw these diagrams and learn what are the types for the words, all from data. So essentially, there's a lot of work showing that neural networks and transformers and recurrent neural networks, convolutional neural networks, that they manage to capture some grammatical structure. So there's people experimenting with neural networks and showing that they learn grammar in the first layers. And essentially, what we would want to do is to make that more explicit, in the sense that making the machine learn diagrams rather than just making it some implicit layer in the middle of the neural network. I guess, yeah, that's a big question. So, but yeah, we're definitely working on it.
Okay, thank you.
Seems like there are no more questions, or if there are any questions, people can still, yeah, we still have time, some time. Okay. If there are no questions, then we can take a break of 8 minutes, and we can come back at 8 with the second presentation from Procheta. And yeah, so meanwhile, stay on, and we can take a break.
Yeah, thanks for the questions.
Yeah, thanks, Alex. Again, thanks for giving a nice talk. Yeah, would you also put up your slides somewhere
yeah.
So that, yeah,
sure. I'll share the slide.
Yeah, sure. That would be great. So I'm just checking if I missed out any questions, or I think, yeah, pretty much. Okay. So are there anyone who wants to announce anything or anything about like an conference or something? Yeah, you can also do that. Yeah, from the participants. So Alexis, I think I can ask a general question. So like the quantum machine learning is being now kind of like there've been some use cases where they've been applying some quantum support vector machines and stuff, yeah, to real use cases.
And that was some people from IBM working with
yeah,
one from the computer science department in Oxford.
Yeah. So what stage is it quantum NLP is in? Like, are there any like any small use cases for real, how do you call it? Like practical use cases or anything? Do you foresee any?
Practical, no. So for now, practical, if you want to do practical NLP, you do GPT-3, you train trillions of parameters. But I mean, what's the state of QNLP? There's a workshop happening next week, and there was one happening last year already. And for now, that's pretty much what the state of QNLP is we're organizing the first workshops on the topic. And there's a few papers. on QNLP, but using essentially just doing the math for what QNLP would look like if we had big enough quantum computers. Here, what we're trying to do is to make it happen on near-term quantum computers.
Okay.
Yeah, for now, there's a bunch of algorithms that could apply if the quantum computers got big enough. And there's a first proof of concept of doing something on a near term, doing something on a computer from today, which is really bad and noisy and all of that.
Okay. So is there anything like an hybrid, like a quantum classical thing of version for NLP2? Because for quantum machine learnings, it's not purely quantum. You can also run on a classical computer, but mostly like an hybrid one where you simulate it.
So yeah, the hybrid part was happening essentially. So I couldn't really go slowly over the actual quantum experiment, but what happens is you have these quantum circuits that you evaluate on quantum hardware, and then the results for the measurements go back to a classical computer that is going to decide the updates for the parameters. So essentially, it's always a hybrid classical quantum loop where the quantum machine gets executed, and then the classical machine decides what to execute next, right? So it's always going to be hybrid, or at least for now, we're not going to have quantum computers alone, right? They will work on the cloud with a classical pipeline around it. And that's what I think it was PyTorch that just released a quantum module where now you can write your pipelines in PyTorch, where some bits of the pipeline are quantum algorithms. So essentially, if from the outside, it doesn't matter whether you're using a neural network or a quantum machine.
Okay, thanks. That's great. You can also share the link here for the next, the school you're talking about for the next week one on quantum.
Oh yeah, I'll share that, the quantum week of fun.
Yeah, sure.
And then I'll send my screen, my slides. I'll send them over by email. Just
sure.
Talk. Quantum week of fun.
Okay. So Michael, is there anything we need to announce? Usually I tend to forget some stuff. So from the PyData side.
Well, not that I know of, except for, unless you have mentioned the code of conduct that was sort of broken in the beginning of the session. But I mean, it happens. It was kind of exciting. For those of you who didn't witness it, we had a couple of Zoom bombers joining the meetup and yelling some unintelligible stuff. So we probably learned from that for the next time to set up a waiting room and select the people who join.
Yeah, I think, but I mean, it's also difficult to distinguish, right? I mean, it's...
well, you could put them in.
Yeah.
You see if they're normal. If they're not, we kick them out. So apart from that, I think, well, usually at the PyData Berlin, we have lightning talks, like informal lightning talks. If there are people who have vacancies in their companies or a project that they'd like to present, we gladly invite anyone to step forward and announce a lightning talk. It could be like a 2-minute lightning talk where you just talk about your recent project or any type of thing that you would like to announce. It's generally an option outside of pandemic times. Right now, it isn't quite an option because we're way too few people, but still, I welcome anyone to step forward and announce anything like vacancies in their departments or in their company.
Or if you're looking for anyone to collaborate on an open source project, I think that's also something. In the past, we had a lot of people who collaborated on a lot of open source projects.
Yeah. Also, DisCoPy is all open source, so
yeah.
if you want to collaborate, feel free.
Yeah,
Cool.
that's great. Okay. Oh, the Cambridge one. Okay, I think I saw this. Yeah. Okay, I think we have all the people, so I guess now we can start with the second talk, which is by Procheta. I think I spelled your name correctly, I guess.
Yeah.
Yeah. So you can go ahead with a very interesting one on socially responsible AI. So you can also do your introduction, like what do you do and
Okay.
stuff.
So
And,
I'm audible, right?
Yeah.
Okay.
So.
So I'm starting then. Yeah. Okay. Good evening, everyone. So today, so first let me give a brief introduction of myself. I am Procheta. I am a PhD student in Dublin City University. And today I will be presenting our work towards socially responsible AI, cognitive bias-aware multi-objective learning. This is a joint work with Devashish Ganguly from IBM Research Dublin. So this work has been accepted in AAAI 2020. So, start. So there are a lot of factors that can cause cognitive bias. The different factors involved are memory, social structure, learning, belief, money, politics. And depending on all these factors, different kind of bias can arise. So in our work, we have specifically focused on stereotyping bias, where the sources are like all the different features that I described earlier, this memory, social, learning, and belief, money, and politics. So the objective of our work is to mitigate this stereotyping bias from AI-based classification models. And so we want a perfect balance between this fairness and the accuracy of the model. That's the objective of this work. So human society has historically exhibited bias through gender and race. There are data, and so now we use the data-driven deep learning models, and they usually tend to pick up those bias from the human-generated content. And that's why we get biased predictions. There are examples like terrorist prediction models, which intend to predict a brown skin colored person as terrorist. Similarly, it has been shown in previous work that suppose for the word embedding, the distance between the vectors like vectors of the words like male and programmer is lesser compared to the distance between the word vectors for female and programmers. For the emotion prediction system, it has been seen that like a female gender is generally associated with the emotions like fear and anxiety. So but this shouldn't be acceptable. And there are a lot of examples in terms of search also. So the first example that I am showing here, this is from Google image search. So if you search about the CEOs in Google image search, so here you can see the top results that we got. So in general, according to the statistics, 27% of the women are CEOs. I mean, 27% of the CEOs are women. But as you can see from the picture, the 11% of the pictures are from the women CEOs. So this kind of imbalance is there. That is another example of query auto-completion. So if you search about, so this is the example from a particular time instant. So if you search about Scarlett Johansson, who is a famous actress, so the query completion examples that the Google shows are like in a body here and workouts. We can say that the suggestion algorithm is prioritizing this appearance over filmography. So what we can do to remove this bias? So first we need to identify the source of bias. So in a simple feature-based model, we can think of removing those features that can potentially cause bias in the model. For example, New York Police Department refrains from using the race of a person to predict the risk of future crimes. But understanding exactly which feature or the combination of features can cause these ethically incorrect responses, that is not always easy. And this situation is far worse in case of data-driven deep learning models, because we rely on the abstract representation of data. We do not explicitly give different features to the model. For example, what to wake, and like there are a lot of different models. In these cases, we can't exactly identify what is the exact feature which is causing bias in the model. So in our work, we basically proposed a model which can remove bias in this kind of AI-based models. So to understand the bias mitigation process, first we need to understand that, first I will define the primary task. So primary task in our work is the basic objective of the AI model. So in our case, we have taken the classification-based model. So basically, we work with the emotion classification problem. So where the input is the embedded vector representation of a sentence, and the output is the emotion levels corresponding to those sentences. Outputs are categorical variables. For example, in our case, this can be anxiety, joy. And primary task is basically learning the association between these input vectors and the corresponding levels. So then we have formulated the mathematically tried to formulate the cognitive bias. So in our case, to understand understand this bias, first we need to understand the social identity attributes. So these social identity attributes are basically the set of attributes which can eventually lead to bias. For example, gender, race, these are the example of social identity attributes, and these are categorical variables. So they can have, like for example, gender can be male and female, emotions can be fear, anger. So so the combination of a subset of these identity attributes and the output levels can eventually cause bias in a model. For example, for the emotion classification task, the association between the female and the fear emotion, that can eventually lead to bias. This is basically social identity attributes, and based on these social identity attributes, we label our bias variables. So in our research scope, these bias variables are basically binary variables, which can be 1 or 0. So with respect to each input instance in the training set, we basically assign one bias response variable. So the bias response variable is 0 if the corresponding social identity attribute and the output level, the primary task output level, doesn't come into the bias sensitive category. For example, if it is about male and fear, then we do not assign that, but then we assign the bias response variable as 0. And it is 1 if it belongs to the subset of categories which can even potentially lead to bias. For example, female and fear. So this is how for each input instance, we assign this bias response variable. So after assigning this bias response variable, then we have proposed this multitask objective learning based architecture to remove bias from an existing model. So as you can see in these models, first in the initial layer is the data vector layer where you input basically the data vectors. Then that input layer is passed through a shared layer. So the objective of this shared layer is to basically transform the input data vector space into a different space where the bias will be less. So after passing through this shared layer, then we have the separate architecture for the two different tasks. So the first task is the primary task learning task, which is in our case the emotion classification task, and the second task is the pseudo bias response generation task, since we have the bias response variable corresponding to each input instance. So the overall objective of this function is the sum of both the primary task objective learning function and the bias response variable function. So this is the overall objective function that I have shown here. The first one, where we have shown this P of y given x, theta p, theta s, that is basically the primary task learning function. And the second one, so again, for the bias, we can have a model can have bias with respect to different kind of social identity attributes. Can have the gender bias, race bias. So for each different type of social identity attribute, basically for each different type of bias, we define separate bias response variable. So for each bias response variable, we have separate bias response generation task. So which is basically this PYIB given X. Now, as you can see that in the overall objective function, we are basically trying to minimize the primary task objective function, and we are basically trying to maximize the bias response variable generating objective function. The reason is that we want to de-learn the bias response generation function, because we do not want association between the kind of, like for example, in our case, between the fear and female. So basically we want to de-learn that. That's why we are maximizing this bias response by using this minus sign, and we are basically minimizing the primary task objective function. So this is an example with simulated data, like what is the effect of applying our bias mitigation architecture. So in this simulated data, we have basically two classes. As you can see, the colors of the these points determines the level corresponding to those points. And the blue solid line basically shows the boundary of the classifier. In the left hand side picture, this the blue classifier is the classifier where we didn't apply any kind of bias mitigation architecture, and in the right hand side picture, the blue line shows basically the boundary of the classifier after applying the debiasing architecture. So this particular data has simulated data has two dimensions only, x1 and x2, and the dataset has basically bias with respect to x2. So as you can see that compared to the left hand side picture, in the right hand side picture, maybe the accuracy has reduced, but the bias is less. I mean, here you cannot directly say what you can say from the left hand side picture, that if a particular point has x2 value less than 2, then always it gets the red level. But that particular conclusion you can't draw from the right hand side one. So that's how the bias gets reduced, maybe at the cost of accuracy, but the bias gets reduced. So now I will talk about the results that we got with a real life data set. So we used this equity evaluation corpus, which was the emotion classification data set. So with corresponding to each, so this was a balanced data set. So there were gender and race annotations corresponding to each sentence levels. And regarding gender, they had annotations for male and female, and regarding race, they had annotations for African American and Caucasian. And for each different type of social identity attributes, for example, male, female, or Caucasian or African American, as you can see that they had equal number of examples. That's what I said, that it was a balanced data set. And the emotion levels corresponding to its sentences were fear, anger, joy, sadness, and neutral. So there were a sentence which didn't have any kind of emotions annotated with that. Okay, so we used basically 3 different versions of this data set. So the first one was the balanced data set, which is the original data set. And we also created some biased data set from this balanced data set. The reason was we wanted to see the effect of balancing data set in debiasing, whether we can actually completely remove bias by supplying balanced data set. So we have created 2 different versions of biased data set, that was SS1 and SS2. In SS1, we have more number of female and fear examples and male and anger examples compared to male and fear and female and anger. And similarly, in SS2, we have more training examples of Caucasian and fear compared to African American and fear. So these are the different approaches we investigated. So the first category of approaches were the bias agnostic approaches, where we basically didn't apply any kind of debiasing technique in the classifier model. And we also used this bias agnostic L2 approach, where we basically added the regularization with the standard classifier. Just wanted to see that adding regularizer can remove the bias or not. Then we used this bias agnostic gender feature approach, where we basically gave gender as an explicit input feature to the model to check that whether that can remove bias or not. Similarly, we also tried to input race as a particular input feature to the model. And we also applied debiased word embedding. So there are standard techniques of debiasing word embedding. So we used debiased word embedding to check whether using debiased word embedding can remove bias from a classifier model or not. So how we can basically evaluate the effectiveness of a debiasing approach. So we proposed a metric called fairness for our for our proposed approach. And we also, and then using basically the eventual objective of a model should be to have both accuracy and fairness higher. So we also proposed a combined app, which is called, we call the gamma, which is basically the harmonic mean of this accuracy and fairness. So how did we exactly measure the fairness? So to measure the fairness, we basically measured the posteriors with respect to different emotion categories and different social identity attributes. For example, if we want to measure the fairness with respect to the feature, with respect to the emotion fear and the social identity attribute gender, then what we measure, so corresponding to gender, we know that there are two different categories, that is male and female. So we measured that what is the posterior of a person being male given the gender is given the gender is fear. And similarly, we also measured what is the probability that a person being female given the gender is fear. Now, basically the fairness is basically the multiplication of these two posteriors. So from the computation, as you can see, that fairness will be higher when these posteriors will be uniform with respect to the different categories. For example, for male and female, if both of them are 0.5 and 1.5, then fairness will achieve the maximum value. So yeah, that's how we measure the fairness, and then this gamma value. So this is the result that we got. So from this result, the interesting observations are that from biased, the first category of approaches are the biased agnostic approaches. So as you can see that using balanced data set obviously reduces the bias present in the model compared to the using the biased data set, but it doesn't completely removes bias from it. So that is the first observation. The second observation is that using gender and race as explicit feature doesn't help to remove bias from a model. Similarly, we have also seen that using debiased word embedding didn't help to remove bias from the classification model. And there is a recent paper in Knuckle 2019. So that also shows that the debiased word embedding technique doesn't help to mitigate bias from the downstream task. They may remove bias from the vector space, but eventually the bias gets carried into the downstream task. So our observation is basically consistent with that paper. And then third comes our approach, where we try to remove bias with the bias gender approach, bias race approach, and the bias joint. So in the joint method, basically we try to remove the bias, gender and race bias simultaneously. So as you can see that in our proposed approaches, the fairness value has increased compared to the debiased word embedding approach and the bias agnostic approaches. So yeah, that's the main and the effect of using, the utility of using the joint approach is that you don't need to train your model 2 times. You can remove all the bias simultaneously. Yes, that is the utility of this joint approach. So that's the main takeaway from this result. Yeah. So in this work, we tried to remove bias from a model where we had idea about the annotations, where we had an idea about the categories with respect to which the model has bias. And we also had the annotations, corresponding annotations for the data, for the training data set. But in future, we'd like to explore techniques where we do not have annotations for the whole data, or we have some partial annotations, and we will try to use that to remove bias from the whole model. So yeah, that's all. Yeah. So yeah. If you have any questions, then I'll be happy.
Wow, that was quite quick. So yeah, I think people can start asking questions. I think we have time for more than a couple of questions. So. So if there are no. Oh, wow. I think if there are no questions, Michael, do you want to add something?
Well, I'm not as familiar with the topic, to be honest.
Yeah.
But I like the idea of, I mean, in my work, I have like a very similar problem, but not necessarily in this domain, but the general debiasing domain. It's, I mean, it is really interesting, and I'm also working on a couple of methods to debias my data set. But like, just because I'm not completely aware of the data set that you've been using, it's very difficult. I mean, you're probably aware.
Okay.
If you're not really.
Yeah. I mean, I remember actually. So, Procheta, are you aware of this IBM fairness tool? Like there are this AIF. So, is it your studies are also part of that?
No, the studies are not part of.
Okay, because I remember like one of my like he's also part of the PyData one, so he actually worked on it at some point. So
Okay.
they would not debias the data, but they would add metrics in such a way that you can always
measure the fairness.
Yeah, you can always have a fairness measurement, and try to actually maximize it. So it's quite similar to what. So yeah, but that was a long time ago. So yeah, and I'm not aware of all the details. Yeah. But anyway, thanks for the talk. We'll just also still wait for people if they want to ask anything related to it. So I think everyone can unmute themselves. Yeah. So please, if you want to ask any question or even any comment, yeah, please go ahead. Okay. Okay. So your work will also, so your talk will also be available as slides somewhere, like, or you can also send us.
I will send you the slides.
Okay, that would be great. Yeah. So is it also on GitHub? Like, if someone wants to try it out, like.
Yeah, there is a GitHub link, so I will send both
Okay.
of that.
Yeah. You can post the GitHub link on Meetup as comment.
Oh, okay. Yes,
I think that would be easier. And others, yeah. And if your talk is also on GitHub, then you can also post that link there.
It's not in GitHub talk, I will send you.
Yeah, sure. We usually have a GitHub where we keep all the PDFs of the talks. It hasn't been updated for some time, so we need to do that again. Yeah.
Yes.
Okay. So anyone from the audience, any comments or anything they want to? Okay, yeah, Debasis, you can go ahead with the question. 1 second. Oh, sorry. Yeah, now I think you can unmute yourself.
Oh, hi, yeah.
Yeah.
Since we have got time for questions, and since I'm a co-author, so maybe I'm not the best person to ask this question, but since we have got time, so maybe we can discuss.
Yeah, sure, go ahead. Yeah.
We can discuss. We have time for discussion. So one of the things that maybe Procheta could elaborate on is like, what kind of how do we plan to extend this work in future? Because you talked about the unsupervised approaches and the semi-supervised approaches. How exactly you plan to do it? So that's question one. And the second question is, we have basically addressed the classification task here. but there are some other tasks in machine learning as well, regression tasks, or I don't know, some other tasks like sequence labeling for natural language processing. So how do you envision that, firstly, does it make sense to compute or to use the same metrics that you already had used in your work? Do those metrics extend easily to the other types of tasks? If not, then what kind of bias quantification could you achieve for those tasks, and how might you mitigate biases for those tasks?
Okay, so there are a lot of questions.
Plenty of questions. Yeah, sorry about that.
Yeah. So for the first question, I think regarding the problem that we can't have annotations for the, like in real life scenario, in most of the cases, we can't have annotations for the whole data set. So one way can be to design another oracle which can kind of predict this social identity attributes using the like few annotations what we have. Then once we have that kind of oracle, then we can use that to apply in our work, like in the kind of architecture that we have proposed, because we need to generate in anyhow the biased response variables. So yeah, that is one thing I can think of now to apply where we do not have any annotations. And regarding the second questions, like since we have done with the classification task, but what will be for other tasks? So obviously, I think that for the other kind of tasks like regression and sequence labeling, we can't essentially use the fairness metric that we have used. Somehow, so we need to somehow quantify, if we can quantify the output, and then basically we can categorize the output, the continuous output, into different levels, and based on that we measure the posteriors. Then we can use something like fairness over there. So basically we have to first quantify the output, the continuous output level, and based on that we need to measure the posteriors in our case. That's what I think.
Yeah, so maybe for regression it's quite simple, because you could treat regression as you could easily transform regression problem into classification one by quantization. So I guess for regression it will be quite similar, but sequence classification is quite a different kind of problem, right? So where you assign label to each token in a sentence. So you have to identify spans of text. Let's say, for example, open domain question answering, or I don't know, named entity recognition, where you don't associate a particular label to an instance, but you associate a label to a particular token or a particular word. So how in that case could bias be computed or mitigated? I mean, I don't want an exact answer, but maybe some ideas in that direction could be helpful.
Yes, for sequence labeling also, yes, we are predicting the sequence label, but there also we have a fixed set of output classes. Based on that, we are predicting the next sequence level. So that's how you can map that into a classification problem, I guess. Because since you have a fixed number of possible outputs, and obviously a sequence labeling task basically predicts the probability that what will be the, most likely next sequence. So there also you have a fix. So the each output dimension can be thought of as the different classes.
Okay, thanks.
Are there any more questions or comments? Okay, seems like not many questions. If so, then yeah, thanks again for the talk. Nice talk presentation, Procheta. And yeah, so I can actually make an announcement about an event which is happening. It's called PyData Global. It's now an completely online conference, which involves all PyData from all over the world. So there are like more than 100 meetups, chapters, local chapters around the world. So this is the one. So I think the CFP is already over, but the program is out. But there are also some open sessions where you can find collaborators to work on a project and stuff like that. So yeah, I ask everyone to check out. And and other than that, yeah, thanks a lot for everyone to join. I mean, we can hang out for some more time because the talks are finished quite early, so we still have some time to hang out. And if people want to announce or say anything or make any like suggestions or anything, would be great. Michael, if you have anything else to say, you can also go ahead. Seems like Michael is okay. Okay, so anyone wants to start a discussion or anything of that kind? Okay.
So since I'm new to this, so maybe I could
Yeah.
ask a few questions. Like how often do you meet?
So the meetup is actually every month. So we do it on the third Wednesday of every month.
Okay.
That's the idea. So it's been quite regular for like almost like 4 to 5 years. Before that, it was a bit, yeah. So,
okay.
So it's been quite, I mean, so we have regular meetups every month. And we also usually have an annual conference every year. And so usually it would be around July or sometimes in August or sometimes in May, depending on the availability. But this year, due to pandemic, we actually had to kind of postpone the conference or kind of cancel it and do it for the next year. Last year we did the conference. It was a joint conference with PyCon DE. It's the largest Python conference in Germany. It's from the German Python Software Verband, like the software organization. And everything is actually, they're all open source, are NGO, non-profit organizations. So yeah, so none of these, so this money which is collected from all the conferences and all the events goes to projects which NumFocus supports. So, so that's the idea. And unfortunately this year, yeah, we had to cancel the conference and hopefully we'll have it next year. And the plan is to have a joint conference again because PyCon is also hosting the conference in Berlin. So we would have a joint conference sometime. We still haven't figured out the dates yet, but we are planning about it. Yeah. So, and apart from meetups, there are also some special events sometimes, like there are some people in Berlin who are like maintainers or main core developers of data science projects like scikit-learn and other ones like Spacey is also based in Berlin. So sometimes we also try to make these special events which are focused on open source developments. So yeah.
Okay, that's good. That's good.
So if you're also a PhD student, or you're done with your PhDs?
I'm done a long time ago. So
okay, yeah, sorry, yeah, then yeah, okay. Yeah.
I graduated out in 2013.
Okay, oh, that's a long time, yeah. So Procheta, you are a PhD student, right?
Yeah, I'm a final year PhD student.
Okay. Alexis, are you? Yeah, I mean, if I'm understanding, you're not finished yet, right?
No, I'm right in the middle of the PhD.
Okay. Yeah. Yeah, I think. Yeah, that's. And so yeah. Anyone wants to ask anything about the PyData stuff? Also, yeah, I can answer that.
Yeah, so you said that you have regular call for papers every year for the conference.
Yeah, exactly. Yeah, the CFP.
So what is the main focus area of the conference then?
To a large extent, it's very broad. So anything under the data science, under the sun of data science, like more. But a lot of times we have more focus on NLP, machine learning, and deployment has been a growing area. And also there are also Python programmers, like Python libraries. Like a lot of people talk about their new libraries they have built, both for Python, data science use cases, or even in general. Last year, because we combined it with PyCon, we had so much of software engineering side also. DevOps was also a big thing, unit testing, and people also talk about a bit about IoT and data science combined. And graph data science is something which we did not have extensively, a lot of talks, but we had some topics related to it. This is something which is also like an emerging area.
Yeah, topic now, right? Yeah.
Yeah, like there is some, I think there was a talk on graph convolutional neural networks, but apart from that, not much. And yeah, there was, and also diversity in data science is also something which people, like a lot of people are interested in, especially in Berlin. And also data science for social good is also a big thing. So these are also the other topics which are also part of the conference. But in general, it's a very broad areas, and because it's spanned over like 3 to 4 days. So yeah, there's like plenty of room for talks, and there are also a lot of short talks, lightning talks, and then there are tutorials. So yeah.
Okay. Yep.
Okay. So if there are no comments or anything for discussion, I think we can end the session. And thanks everyone for joining, and special thanks to Alexis and Procheta for the talks again. And yeah, we continue to have you on the meetup. Hopefully we might have a physical meetup soon.
Yeah, I hope so. I mean, thanks again for the organization and everything.
Yeah.
I was kind of sad I couldn't come to Berlin to.
Yeah, I remember you did mention that. Yeah. Yeah. So yeah, and thanks again, and maybe we can see again in the next month. So yeah, this meetup is every month, and we do it on a third Wednesday of every month. So hopeful to see you.
Oh, can you also let me know once you get the recording up?
Yeah, sure. Yeah, we would first send it to you both, and take a view, and then then upload it to the YouTube channel. Yeah.
Beautiful.
Yeah, great. So yeah, thank you everyone, and then have a nice evening, and yeah.
Yep.
Ciao.
Thank you.
Ciao. Cheers.
Thanks, guys. Thank you.
Yeah. Bye.
Bye.